look at the relationship between position versus time and velocity versus time graphs. We're going to find the velocity from displacement, and then alternatively we'll find the displacement from velocity. Then we'll extrapolate to acceleration versus time. Finding velocity, as we saw, was finding the slope of the position versus time graph. So for this example, between 0 and 2 seconds, the slope of the position graph is x final minus x0 over t final minus t0, which gives you 2 meters over 2 seconds, which is 1 meter per second. It's a constant velocity. We see it's just a constant slope. Now, if we want to find the displacement, if we have the velocity graph, then we recognize that the displacement is the integral of velocity versus time. In general, we may have some velocity function. For this case, we just have a constant velocity over our time intervals. This means we can simply count the boxes under to find the area under the curve to find the integral of velocity versus time. Between 0 and 2 seconds, delta x is the integral, so the area under the curve is 1 meter per second is the velocity times 2 seconds, so that comes out to be 2 meters, because the seconds cancel. We can do a similar thing if the velocity is negative, as it is between 4 and 6 seconds. If we have the velocity curve, we can find the area under the curve, and that will give us our total displacement over that time increment. So we see for the between 4 and 6 seconds, we have a velocity of negative 2 meters per second. That lasts for 2 seconds, and that gives us minus 2 meters per second times 2 seconds, which is minus 4 meters. And that checks with what we see from our position graph. We have the final is minus 2 meters minus the initial, which is minus 2 meters, which gives us minus 4 meters. We can derive our kinematic equations by recognizing that displacement is the integral of velocity versus time, and similarly, velocity is the integral of acceleration versus time. If I have constant acceleration, this integral is pretty easy to do. I just have v final equals the integral of a dt from t0 to t final, which equals at plus v0. Recognize that v final minus v0 is just delta v. Similarly, we can find x final as the integral of the velocity function dt. Here I've just substituted in for the velocity function at plus v0, then taken the integral. I get x final equals 1/2 at squared plus v0t plus x0. In general, velocity is a slope of position versus time. Acceleration is a slope of velocity versus time. Velocity is the integral of acceleration versus time, and displacement is the integral of velocity versus time. We derive our kinematic equations for the case of constant acceleration. Now recognize these equations are only good for that case. If you have some acceleration that's a function of time, you actually have to do that integral. Thank you kindly for coming. See you again next time.